Hi, Mr. Simmons here. This is the video to go through the textbook answers to topic P8.1 Vectors and Scalars. So for the learning objectives for this topic, you should know what do we mean by displacement, what is meant by a vector quantity, what is meant by a scalar quantity, and how to represent a vector quantity. So the key points here are that displacement is distance in a given direction. A vector quantity is a physical quantity which has magnitude and direction. A scalar quantity has magnitude but no direction. And a vector quantity can be represented by an arrow in the direction of the vector and of length in proportion to the magnitude of the vector. So the study tip is that force diagrams usually show more than one force. For this reason, the forces on a diagram should always be clearly labelled to identify the force. Force diagrams do not always need to be scale diagrams, but if a diagram is a scale diagram, the scale should be shown. So for example, 10 millimeters equals 1 Newton, where the three little lines there equals represents. So question 1, you should have got the answers for these already via email, but I'll just go through them. State what is meant by the magnitude of a vector quantity. The size of a quantity is its magnitude. State the difference between a scalar quantity and a vector quantity. A vector quantity has a magnitude and a direction. A scalar quantity has magnitude only. So question 2. Look at the journey shown on the map in figure 1. So I've got figure 1 here. If the displacement arrow, that's this arrow here, shown in black, represents a displacement of 10 kilometers, use the map to estimate the approximate distance travelled by the student on their journey to school. So the distance that they travel is shown by these red arrows here, and what you need to do is to come up with a way of approximating how long these arrows are if you add them together. Now what I've done is I've printed off, just by print screen grab of the kerboodle textbook, onto paper, and I'm going to go through this with you on paper because it's actually very difficult to kind of show you on screen here how to do this. But just to give you a word or two about actually working on the computer, I know that some of you having difficulty accessing computers because there might be like lots of you in one household all trying to do work on one computer or only a couple of computers between several of you. So it's a good tip anyway that you can, if I just flick to the kerboodle textbook here, you can just actually print screen. You should have a print screen button on your laptop or computer, and if you've got a printer you can then just print that section of the textbook that you can then work with on paper. So I'm going to change to camera looking at paper in a minute, paper copy, and I'll show you how to do this approximation of the distance on there. Okay, so working on the bit of paper here that I've printed off, and I've done a very technical job of, you can see, of sellotaping bits together that I've printed off just to get all of the textbook pages that we're working with in here. So question 2 is what we're looking at. So look at the journey shown on the map in figure 1. If the displacement arrow represents a distance of 10 kilometers, use the map to estimate the approximate distance travelled by the student on their journey to school. So what we need to do is actually estimate the length of all these arrows added together. Now there are several different ways you could do this. You could put a ruler up against them and you could sort of wiggle the ruler around the line to work it out that way. But actually the easiest way to do it, and this is something that was shown in the videos that were linked to the beginning of this week's work on the document that I sent out to you, is to just use the edge of a piece of paper. So if you put a bit of line paper, is pretty useful. If you put the beginning line at the edge of the paper there, and then you just move it so that it follows the curve, and if you just keep putting a pencil against it like this and moving it around bit by bit, you can follow the curve of the arrow and you can go all the way along . Now the smaller the little sort of jumps that you make here, actually the more accurate this will be when you're following a curve. This is where I wish I had slightly better video editing technology at my disposal, then I could speed this bit up. That's what the real professionals do, isn't it? So that's gone to there. Okay, so I have my starting point on this line here and my end point there. And all I need to do is match this up against the line here, which we know is 10 kilometres. So if I put the beginning of that line there, so that's 10 kilometres, then I can move that back along, put it up against there again, and that's going to be 20 kilometres there. So where I got to is probably somewhere around 20 to 21 kilometres. So I showed you how to do this by printing off on a piece of paper, which I've cunningly sellotaped together. But of course the other way of doing it, if you have a tablet, you could actually do the same thing on a tablet. Sorry, this is going to be a bit flickery. You could actually do the same thing, just lining the piece of paper up against your tablet. You might find this a bit fiddlier because you might find that you sort of move the screen around a bit as you're touching it and so on. But it is possible to do that using a tablet. You could even do the same thing up against a computer monitor as well. Looking now at question 3, it says a small object is acted on by a horizontal force A of magnitude 15 newtons and another horizontal force B of magnitude 12 newtons, which acts in the opposite direction to A. Draw a to-scale vector diagram showing forces A and B acting on the object. Now again, there's a couple of ways that you can do this. You can either use a pencil and a ruler. So, I mean, if I was to do it as 1 centimetre is 1 newton, then I would get quite a large diagram to go 15, and then I wouldn't be able to fit my next arrow either side of that. So I need to shrink the scale down a bit. So I could use a scale, for example, of 1 centimetre is 2 newtons. So I could go, starting there, I could go 2, 4, 6, 8, 10, 12, 14, and then halfway that would be 15 newtons, and I could draw that as one force A in that direction, and then I need my force B to be 12 newtons, so put my ruler up against it again and I can go 2, 4, 6, 8, 10, 12. And that would be force B, and my scale then is that 1 centimetre is equivalent to 2 newtons. Okay, so A there is 15 newtons and B there is 12 newtons. Another way of doing it though is to just, if you don't even have a ruler, is to just use a bit of paper again, like I did before. So just a scrap bit of paper. If I take the lines on this bit of scrap paper, I can do the same sort of thing as I did with the ruler. So if I start there, and I can just count 2, 4, 6, 8, 10, 12, 14, and then that would be 15 newtons there. So that's my first one, A. And then my second one, B. Just starting at the same point, 2, 4, 6, 8, 10, 12 newtons there. Okay, and then my scale. Now, I happen to know that these line widths here are about 8 millimeters. You can actually check that using the textbook itself. If you printed it and it's printed out 1 to 1, you can see here scale 10 millimeters, that's 1 centimeter equals 10 newtons, and I can just put this up against there and you can see that the lines are about 8 millimeters between them, the gap. So my scale on this diagram is that 8 millimeters is 2 newtons. Okay, question 4. So a force A of 48 newtons acts on a small object as shown in figure 4. Copy figure 4 and state the scale you have used on your diagram. So I can do the same sort of thing using my bit of scrap paper again. So if I want to make my line 48 newtons, if I just make each division on here equal 12 newtons, so that would be 12, 24, 36 and 48. So there's my force A, and my scale is 8 millimeters to 12 newtons. Then question B says add a further arrow to your diagram to represent a force B of 36 newtons acting on the object in a direction at right angles to the direction of the 48 newton force. So all I need to do now is put my bit of scrap paper up against the beginning at 90 degrees, line it up with a line on the paper, and using the same scale, and you can see that obviously it's the same lines that are on here anyway, I can go 12, 24, 36. So that is now my force B, drawn to the same scale. Okay, I'm back here in the virtual world of my laptop screen, so I've just shown you on paper that we estimated the total distance of the journey around those red arrows to be somewhere between 20 and 21 kilometres. And for question 3, a small object acted on a horizontal force of 15 newtons and another horizontal force B of 12 newtons in the opposite direction to A, and I showed you how to draw a two-scale vector diagram showing forces A and B acting on the object. So it's any scale diagram with a ratio where B to A is 1.25 to 1, or where B is 15 newtons, sorry, B is 12 newtons, A is 15 newtons. So therefore the arrow, hang on, that mark scheme is wrong. It says therefore the arrow for B is 1.25 times the length of the arrow for A. Actually it should be the arrow other way round. So it should say the arrow for A is 1.25 times the length of the arrow for B. That momentarily threw me there. Sometimes they do make mistakes in the mark schemes for these textbook questions. So I've drawn a similar thing on here to show you the scale. This time the scale is 4 millimeters to 1 newtons on these arrows here. Question 4, again I went through this on paper with you. So depending on the 48 newton arrow length, it says copy figure 4, state the scale you've used on your diagram. So depending on what scale you've used, they've given an example here, a 60 millimeter arrow would be a scale of 10 millimeters equals 8 newtons. I use different scales to that. And then for B, draw a second arrow pointing downwards from the object along the dashed line, which should be 0.75 times the length for arrow A. So on this diagram here we've got a scale of 1 millimeter is 1 newton, so that line there for A is 48 newtons long, and the line for B would be 48 millimeters long, representing 48 newtons. The line for B would be 36 millimeters long, representing 36 newtons, but again I use different scales to that on paper. Okay, so we're done here. Thanks if you've watched these videos all the way through for each one with your work in front of you. You're doing extremely well. I'm glad I'm not wasting my time completely, and stay safe.